Hello, welcome back. Today we're going to continue talking about constraint satisfaction problems. So at the end of the class of today, what we're going to do is to show how constraint satisfaction problems can be solved with generate and test. You should be able to show how that works and the complexity of it. Show how constraint satisfaction problems can be solved with search, and explain and trace arc consistency of a constraint graph, and show how domain splitting can solve constraint problems. So here's the generate and test. So if you remember in mathematics, there's this cross product. And so the domain here of D is the domain of so you have variables v1 to vn. The cross product of this is the set of all tuples, the set of all n tuples. So that's what we're going to mean here. What we're going to do is we're going to generate all of the n tuples. So here is the domain of A, B, C, D. So A1 can be 1, A can be 1, B can be 1, C can be 1, D can be 1, and E can be 1. Another assignment is everything's 1 except E is 2. And another one is actually E, all of them have value 4. So we're going to build up this cross product, this space of assignments, and then we're going to test whether the constraints are true. Okay, and we can implement this with n nested for loops. So in here, we're going to do this for each A in domain of A, and then for each B in domain of B. I'm going to go so on for each C in domain of C, all the way up to for each E in domain of E. And we're going to test all the constraints, and if they're all constraints are satisfied, we're going to return the tuple of A, B, C, D, E. Okay, so think about that. And what I want you to do is in class, we're going to talk about how many assignments need to be tested for n variables, each with domain size D. So what's the size of this? What's the complexity of this? Okay. So it turns out this is not a very sensible algorithm. The number of assignments to a Sudoku problem is just enormous, even though we can actually solve it reasonably well in other ways. So instead of that, another algorithm we're going to do is to systematically explore D by instantiating the variables one at a time. So instead of assigning all the variables, we're going to assign them one at a time. And we're going to evaluate each constraint predicate as soon as its variables are bound. So as soon as we can evaluate something, we're going to do it. And any partial assignment that doesn't satisfy the constraint can be pruned. So as an example, we have variables A, B, C and domains of 1, 2, 3, and 4. And just look at this constraint, A is going to be less than B. So if you look at both of them have value 1, well, we know that that's inconsistent with it. It doesn't matter what C is, it's inconsistent with it. If they both have value 2, if A is 4 and B is 2, they're also inconsistent. So in here we can prune these very quickly. Most of the values of A and B do not satisfy A is less than B. And so now we can prune that. We're only going to check C for those ones that satisfy that. That's the idea. So let's write that down. So assignment A is 1 and B is 1 is inconsistent with the constraint A is less than B, regardless of the value of the other variables. And so we're going to prune it then. We're going to prune early and prune often. So pruning off the space is going to save us a lot. All right. So what we're going to do is we're going to solve it as a graph searching problem. So a node is an assignment of values to some of the variables. Okay, so we're going to have this. So that's what a node is. And suppose the node is this assignment. We have this assignment that's a node. So what we're going to do is we're going to select the variable that isn't assigned in n. So we're going to select a variable that isn't assigned. And so for each variable in the domain, we're going to add that to the neighbor if it's consistent. If it's consistent with the constraints that can be evaluated. So we're going to evaluate all the constraints we can possibly evaluate, and if it's consistent, we're going to do this. Okay, the start node is going to be the empty assignment, and the goal node is, well, it's an assignment to all the variables. That's all we need to do is a total assignment, and by the way we've constructed this, it's going to satisfy all of the constraints. Okay, and then the search space depends on which variable is selected to be assigned for each node. And in this, there are no cycles or multiple paths, so there's something we looked at when we did search we don't have to consider here. There are no cycles or multiple paths to a node. So here's an example of doing this. So we're going to start off with the first node here, with the empty assignment, and then we're going to assign, let's suppose B. B is 1, B is 2, B is 3, and B is 4 might be the 4 nodes. Now let's look at B as 1 in here. So now we're going to look at, now we might want to split on A. So now I can do A as 1. And if we do that, we're going to find that's inconsistent with what we know. Okay? That violates this constraint. We can do A as 2, and A is 3, and A is 4, and we can prune all of these. They're not going to be consistent in here. Similarly in here, we could, for B as 4, we could split on C as 1, C as 2, C as 3, and C as 4, and all those are again pruned. Okay, so now I've really cut down the space here. Just by looking at 2 levels here, we can prune a lot of the space. If we look at B as 2, we can now look at A as 1. Well, that's good. So now I can look at C as 1. Now that's inconsistent with B as 2, C as 2, C as 3. All of a sudden we found a solution. And C is 4. That's also a solution. Whereas all the rest of the A's values are inconsistent. A is 2, A is 3, and A is 4 are all inconsistent with it. Okay, that's what we're going to do here. We're going to look at all of these domains and we're going to find out, there's something under there. And we're going to find 2 more solutions. So that's what we're going to do here. And we've not split it on when we had all these ones where there's ones on the left. We're not splitting on C, so we're saving a lot of time here. If you do constraint A is less than B, B is less than C, and C is less than D, we're going to find out that, again, it's going to be pretty clear that when we split on B, right, when we start off with a node here, we're going to split as B as 1, right, we could prune all of these, right, because B can't be 1 because of all the values for A. Okay, so we're going to split all the values for A and we're going to prune them. Again here, B is 2, etc. So when B is 3, well, it turns out it's a good idea to split on C. C is 1, so now this is the assignment. C is 1 and B is 3. And that's going to be inconsistent because B is not less than C. Okay. And another example I want you to play with is, look, this constraint here. There's 5 variables here. A is less than B, B is less than C, C is less than D, and D is less than E. So if you do this, you'll find out that we can pretty soon prune all of these variables in doing this. Okay. Oops. All right. And here's an example we're going to do in class. Variables A, B, C, D, E represent the starting time of variable activities. The domain of A is 1, 2, 3, 4. The domain of B is 1, 2, 3, 4. The domain of C is 1, 2, 3, 4. The domain of D is 1, 2, 3, 4. Okay, all the domains are the same here. And here are the constraints. B is less than not equal to 3, C is not equal to 2, A is not equal to B. And let's look at a few of these that are sort of interesting. Let's look at this. C is less than D. So C is less than D. If we know that, then C cannot be 4. Just from looking at that, C cannot be 4. Because there isn't any D that works for it. And D cannot be 1. Cannot be 1 because there's no C that's less than 1. Right? Similarly here, if you look at this one here, E cannot be 4. And C cannot be 1 here. So C cannot be 1 and E cannot be 4 because there's no values in the other domain. So that's what we're going to look at next time. So we keep rediscovering then when we build the search trees. We keep rediscovering the same facts. I mean, building a search tree is much more efficient than generating tests, but it's not as efficiently as we can do. We can do better than that by pruning domains as much as possible. We're going to look at that in the next class.